This is Hamid. Hamid asked for permission to record. Okay. Yes, I've allowed you to record. If you want to record, just let me know and make the request to record. Once you make the request, I will okay it. Okay. So let's open. I've sent 3 drawings. There's a one I call swim presentation on hydrology. That's what we're going to start for today. Okay. Let me share my screen. I don't think my screen is being shared. Okay. Before I go to the first outline I have here, let us take a look at a presentation my colleague came up with, and it's really cool. Now, let me just share some idea with us about this is what we're going to be doing today. The topic, this is the course outline. We're going to talk about drainage. We're going to talk about the different types of drainage systems. We're going to talk about how do you characterize your catchment. What are the elements of an urban drainage system? The pipe, the pump, the outlet, the dividers, the swell, the CSO, the combined sewer overflow, and everything. We're going to talk about a little bit of hydrology, talk about and its associated words, such as infiltration, percolation, evaporation, rainfall. Now, ideally, we're going to go through all these things when we are doing physical training. We have full 2 days of 8 hours. But the online training, we have tried as much as possible to take away everything that has to do with something you can read and understand. So whatever you're going to read and understand, I'm not going to lay emphasis on it. I'm not going to talk about it. I only go to those key things that I know that are very important. Now, if you're a water person, you know this. This is the normal hydrological processes. Water comes down, precipitation comes down. Some goes back up through transpiration, while others go back through evaporation. The remaining one goes into infiltration. Infiltration, there's a deep infiltration, there's percolation. Some goes into the groundwater, gums flow on the surface. So for stormwater, we were interested on the runoff, surface runoff. And that is the one that, out of the total that comes on, goes down, it's only a percentage that generates runoff. And that percentage is a function of the level of the catchment area. Is dependent on 2 things. In fact, it's dependent on the level of rainfall, depends on 2 things. Number 1, the intensity. The intensity in Lagos is about 140, 150. In Abuja is 100 millimeter per hour. In Maiduguri is around 70. Okay, sometimes 60. In Castina is about 80. And then in the Niger Delta, oh my goodness, it's about 200. So is a factor. So now, number 1, intensity of rain is a factor. Then the second factor is what the area contributing to runoff. The larger the area, the higher the intensity. Now, in talking about the area, it is not the total area, rather the impervious area. In other words, the area that is not allowing water to go deep. That's why in a garden, there's what we call runoff coefficient. Depending on the kind of surface, the runoff coefficient varies between 0 and 1. The higher water can penetrate a medium, the lower the runoff coefficient. Like a garden, the runoff coefficient of a garden is between 0.1 and 0.2. The runoff of a roof is between 0.5 and 1. Normally, we don't say 1. It's impossible to say 1. You can say 0.98. The reason being that, in as much as the roof is impermeable, but we felt that there could be some level of evaporation and maybe kind of backflow. I want to say transpiration, but the roof cannot transpirate. It's only green area that transpirates. Okay. So that is that. So let me explain. Let me lay a foundation. This is when we talk about types of drainage. There are two types. They are what we call separate system and a combined system. Okay? Or better put, there's a foul sewer system. There's a stormwater system. There is a combined system. There's a foul water system. There's a stormwater system. Then there's a combination of two of them. Now, the foul water system and the stormwater system, we call them separate system. Then the other one, we call it combined system. The separate system is what you have on your extreme, on your left. It means that the sanitary wastewater coming from the household has its own line. It has its own design. Okay, look at it. It has its own design. Then the stormwater coming from the roof, coming from the garden, coming from the compound, coming from exposed area is now a stormwater line. It has its own design. Look at this one. This one is coming from just water. This one is coming from street catchment. This one is coming from roof catchment. This one is coming from garden. You can see that this one has its own line, usually made of concrete, and the minimum size is usually 0.6 meter, and it can go as high as 1.5 meter or 2 meter, or like the one my friend did in Asaba recently. It's a 3 meter drain. 3 meter drain. 3 meter drain. That's what he did in Asaba recently, because Asaba is a very low lying area, very close to the River Niger. And in most places I've seen, especially in most of these estates, they don't go below 600, but most times they undersize it. Ideally, it should be based on the catchment, you should be narrowing towards 0.75, 0.9, or 1 meter. Whether you're using circular, or you're using rectangular, or you're using trapezoidal. All we want to do is the surface area. So whichever area you are using, whichever type of drain you are using, is just for you to capture the surface area, 200 pipe or 150 pipe. The standard says that you must not use less than 150 mm pipe for a sewer line. Is a standard I'm going to share with us. If you are doing a sewer system, even when you design and you find out that a 4 inches pipe or a 100 mm pipe can do, the standard says you are constrained by the standard to use 150 mm. You are constrained to use 150 mm. So that's the standard. For the stormwater, there might not be any standard, but the standard as regards that is that you must provide manhole in certain points in between 40 meters and 90 meters. Now, don't worry yourself about all the standards. I'm going to share the code and standard with us, and you're going to read them and you're going to find them. They are all there. And the good thing is that in the Nigerian code and standard, the people that designed it mentioned Swim as a software that can be used to do design. Yeah, they mentioned it. So before I go ahead, I think I would like everyone to have this material. So I'm going to pause now and share these materials and make sure everybody got it. So in the next 2 minutes, let me share I'm going to share the highway design manual with us. Please, at any point you have a question, make use of the chat box. I can see some people chatting me up. So let me quickly go there. Attend to them.
Do you want to be a part of the letter?
Okay, sorry. Please send me material. Okay, have your email. Please allow to. Okay, I'm sorry, I didn't see it on time. Here you go. People have not requested to record, so maybe you're going to depend on my YouTube. I usually put these things on where I can put them. I usually put them there. The person that made requests for record. I can't find you. Okay, allow to record. Okay. Allow to record. Okay. Okay, here you are. Okay, so okay, that is that. So the chart, let me upload. Now, quickly go to the chart now. I'm uploading the Ministry of Work Highway Design Manual now. How many of us have accessed the material on in the cloud?
Hello.
Hello?
Okay. Hello?
How many of us have accessed the material on the cloud? How many of us have issue accessing it? Because there's more in there. All what I'm sharing with you is already in the cloud. But what I'm sharing here for those who don't have access to it, there's a link in the chat box. If you click on it, it will take you to my Google Drive. I've given you permission to access my Google Drive. There you go. So if you click it, you have access, it will take you to Drive. And for some of us who don't have Drive, a cloud, account in the cloud, I want to encourage you. It's the in thing now. Nobody is carrying USB. I can't remember the last time I carried USB again. I don't need it. All information you have, and if you have a Gmail account, you have a free 15 gig online, free. You have 15 gig if you have a Gmail account. 15 gig, it means you can upload all your most important file, maximum of 15 gig online, you can upload it. So the idea is that if peradventure, God forbid, something happens to your laptop, all your files are safe. That's why you see all these high-tech, the new industries, the new companies now, they everyone work from cloud. Like the latest Microsoft now, you don't need to buy it, you don't need to download it. Each time you want to work on it, all you need to do is to log in into the internet. You work, as you are working, it's saving automatically. And when you finish working, instead of saving in my document, you save it in my document, but hosted in the cloud. So I want to encourage you, our engineers, we must go into this cloud thing. You must have a cloud account where you can upload every of your thing. Those ones are relevant because if you exceed 15 gig, it means you have to buy. It's cheap anyway, but then to avoid that overhead, limit your files, get those important files. They are not, some of us, our most important file is no more than 2 gig or 5 gig. All you need to buy is to buy 5 gig airtime megabyte, and then you take it up there. And any day you want, you can go and take it down. So that's just my piece of advice moving forward. So here you have the SIWA again. You see we have the single system and the combined system. Now the combined system simply means that because of space and because of finance, but with high-tech technology, you can actually combine your sewer line. When I say foul sewer, I'm talking about what is coming from your household. Some people call it sewage, yeah? The one from toilet, the one from bathroom. That is your sanitary sewer. You can use the word interchangeably. Sanitary sewer, foul sewer, sewerage. Sorry, in local parlance, we say shit in broken, but forgive me for the vernacular. Shit. That is what you call sanitary sewer. Now, you can actually design your system, but it's not we can't do it in Nigeria because we lack the technology, we lack the capacity to do it. But in some countries, like in New York, like in London, what they do is that the same line can carry foul sewer and it can also carry stormwater. How do they do it? There's what we call dry weather flow. Dry weather flow is that when there is no storm event, and when I say storm event, I mean when there is no rain. When there is no rain, what flows in the pipe is what comes from your house, is the sanitary sewer. Then once there is storm event, then what they do is that they have a control device that will quickly divert the foul sewer into the treatment plant. And if the storm meets up with the sanitary sewer, they have what they call a control device and interceptor. such a way that the sewage, the flow, what they call throttle flow is the one at the bottom most, will now flow into the treatment plant, while the upper one will overflow into a holding pond. Now, after the rain, they will open up the holding pond such a way that the upper, the one that have decanted, the free, the less polluted one will flow into a water body, while the one that is now polluted, the sewage, okay, will now flow into the treatment plant to be treated. Now, it is not a common thing to do. In most cases, in 90% of the cases, it's a separate system where you have a storm sewer and a sanitary sewer in most cases. But in some specialized cases, you can still have the combined. So in this drawing, you will see that the sanitary sewer comes here and then flows here, where it goes through a grease block chamber. And then this is a treatment plant. It goes into a treatment plant. And then after it is treated, it will go through a flow, a CSO related bypass, and then goes into the open body. Then the effluent is what goes out of the treatment plant. Influent is what comes in. So the effluent, after being treated, will also be discharged at this point. Some of us cannot see it, but it's there at this point. Why the stormwater? Stormwater doesn't have to go to the treatment plant. It flows directly into the open water. Like in Abuja, most of the stormwater in Abuja goes into the Jabi Lake. It goes into the Jabi Lake. The way Abuja is designed, at least for phase 1 and phase 2, Jabi Lake is a major holding body. Then the other lakes, other rivers, like there are a couple of them. I can't remember their names, but there are a couple of rivers, open bodies where this water flows in, because it flows in there because it's expected it's not polluted. The BOD might be, the BOD, biological oxygen demand, might be high, but it's not as high as the sanitary sewer. The sanitary sewer, the BOD can be as high as 300 milligram per liter to 400. When we say 300 to 400, we're talking about the amount of oxygen required to treat it. While the one for stormwater can be as low as 50, 60. It's very low. It's not too high. Meanwhile, remember that the oxygen content of a clean water is about 8 milligram per liter. The oxygen content of a clean water. So when the oxygen content, the oxygen requirement goes high, we say that water is too polluted. When it requires a lot of oxygen to treat it, so when something is 400, it means it's by 400. So for you to treat it means you need a lot of energy. Okay, so for the combined system, you see this house here, that both the sanitary sewer and the snow melt and the water coming from the roof and the water coming from the industry, they all flow through the same pipe. And when they come here, there's an interceptor, something that separates them. The ones that are not too polluted flows down into the stream, while the ones that are less polluted, that are more polluted, goes towards the headwork of the treatment plant. Even at the headwork, some level of technology still takes place that makes sure that only the highly polluted ones go to the treatment plant. The danger is that if it goes into here, into the treatment plant, it will distort the biological equilibrium. Because in treatment plants, they use microorganisms to treat to eat up the waste. So if you now give them something that doesn't have nutrients, it can create what they call a shock. It can create a shock, and then it means they have to start building again. It takes them about 7 or 14 days to build that equilibrium again. We're not going to go into them. So this is just what I'm saying about. This is a house drainage system. You see that the sewer line is different and the stormwater line is different. That's just an example. Then you see the stormwater drainage system. They are all separate. This is a separate system. The stormwater is different. The sewer pipe is different. It's just to lay a foundation. And here you can see this is typically a stormwater. This is a stormwater channel, and it can come in different shape. It can be rectangular. It can be trapezoidal. It can be rectangular. It can be hexagonal. It can be irregular, and different shapes. So we'll not talk more about this. This is about the software we're going to use. These are the components of this is what the software looks like. The swim software. It has catchment, it has node, it has links, it has rain gauge, and it has outpour. Outpour is where the water discharges into an open body. So what are the steps you need to take if you want to design a drainage system? Whether it's urban, whether it's sewer and stormwater are the two components of a urban drainage system. When you say urban drainage system, they are made up of two components. It characterizes of two components: a sewer drainage system and a stormwater drainage system. So what do? You visit the site, you survey the information, then you characterize the catchments. No two catchments are the same. What is this catchment? Is it a garden? Is it made up of green area? Is it made up of hardcore area? Is it made up of a combination of two? Okay, that's why let me give us something that happens in Abuja. When you go for approval, building approval, they always require you that your building should be less than 50% of the plot of your land, of the building area. And if you go and say you're going to use, if you don't have a lot of green areas, they will also query your building submission. The idea is that they want you to have as much as possible enough green area, because green area produce less runoff. Green area allow water to percolate. The runoff coefficient of a green area is less than 0.2, sometimes 0.1. What 0.1 means is that if 100% the amount of water that generates runoff is only 10%, 0.1 means 10%. So what it means is that if everybody will adhere to that code, that standard, it means that all the water falling inside your compound, for instance, in your house, 50% of them or 60% of them will not leave your compound. They will percolate. What is the implication? If all of them are allowed to discharge into the urban drainage, then the size of that urban drainage will be so massive that it will be unrealistic. So that's why you see in development planning, they will encourage green areas. They will encourage what do you call it? I want to say water, flood areas, flood green areas. The reason is that these are the areas that will ensure that the size of the urban drainage system is not is not undersized. To make sure that the size, because now, for instance, in Abuja was designed in 1978. So they've already envisaged, I think they use about 0.5 for the peak runoff for Abuja, for my experience. I'm not too sure, I wasn't there. I was not part of it. But from what I've seen so far. So in Abuja, they assume that all the rain, all the storm events in Abuja, that 50% of them will only generate runoff. So if you build or you do something and you don't conform to that standard, it means you are introducing excess shock. You are introducing excess shock into the urban drainage system. And that's also why it's good to adhere to land use. Land use is also a way of telling you that this place is low density area, this place is high density area, this place is medium density area. If this place is high density area, it means that for a certain plot of land, we are going to go up. It means we expect a higher number of persons. So for the same house, for the same area of land, let's say 1,000 square meters of land, you can build a 4-story building that will house 100 persons. But in a low density area, that same house will be a bungalow and will house only 10 persons. So you see that the sewage coming from 10 houses can be 1 cubic meter. For instance, if I'm using 100 times 10, 100 liters per person per day, that means 1 cubic meter. But in a high density area, you're talking about 100 times 100, that means you're talking about 10 cubic meter. So the pipe size there will be bigger, because from planning, they've already characterized this as a high density area. So when they're doing the design, they know that this pipe has to be huge, just like in central area in Abuja. Those of you in Abuja, in central area, it's a high density area. That's why you can build 5-story building. You can build in some places in Abuja, along Jabi, Gwarimpa, you can't build anything less than 6-story building there. That's the standard. If you go to FCDA, then a plot of land between Banex and Gwarimpa, that Kado, Gwarimpa Road, for those in Abuja, sorry for if you're not in Abuja. If you look those areas on the 2 lanes, you only see 4-story, 5-story buildings. because they've already provided a sizable drain system, both for urban drainage and both for stormwater and for sewer. But if you do it in places like Karishi or Lugbe or Kuje, where they've already provided, let's say, 200 mm pipe for the sewer line, even though there's none there anyway, because they only designed for phase 1. So if they've designed for that, and now you start building 10-story building in Kuje, by the time all the people in 10-story building start producing wastewater, that pipe will not be effective. That pipe cannot take it. That pipe was not captured ab initio in the design. They didn't see it as a high density area in Kuje. So that's why you cannot go to Kuje now and you build a 5-story building or a 2-story building. Except in the last 2 years, when they've started allowing 1-story building. Because they've already envisaged what the place is going to be. Meanwhile, gentlemen, we are talking about where things are done the standard way. I know many things are wrong being done in Nigeria. I've seen it. So I'm not going to complain about it. Because all these places I'm mentioning, they've not done any design anyway. So when they're doing design, I wonder what they're going to use. Although what they're going to do now is to use what is existing. They will now look at what is existing now, and then they do a sort of backward engineering. Now, I know that this place is built up. I know that this place is having 10,000 population equivalent. So all I need to do is to multiply, okay, each person is producing 100 liters per person per day. I multiply 100,000 by 10 liters, and then I convert it to liter per second. That will give me my size of my pipe. We're going to do that shortly. So the next thing you do is you talk about the hydrology of the area. What is the hydrology of the area? Hydrology means what is the precipitation, what is the weather information. That's all I'm talking about. Hydrology of the area means what is the weather information. And when we say weather information, I'm talking about the rain intensity, because the rain intensity is what will generate runoff. The next thing is the hydraulics. In other words, you are the one to do this now. The hydraulics means the pipe sizing. Based on the hydrology, you do the hydraulics, you do the pipe sizing. And for you to do one pipe size, let me say it here now, say it very loud. Whether you are doing gas, any kind of fluid, there are 3 things you need to get your pipe size. The flow, which you are trying to contain. The slope of that area, because the steeper the slope, the higher the runoff. Then the next one is the pipe material. And when we say pipe material, we're talking about the roughness of the pipe. Some people call it the K factor. Some people call it the Manning M. Some people call it, there are different names they call it. But the word, some people call it frictional factor. So when you call it frictional factor, you call it K factor, you call it roughness factor, you call it Manning N. All you are trying to say is, what is the characteristics of this pipe relative to flow? So 3 things you need to design any pipe. What is the discharge? What is the, if you have a pen, you can write it down. What is the pipe characteristics? And then what is the slope of the area? What is the slope of the land? The steeper, the higher the flow. So the next thing you do is what are the conventional methods for drainage system? There's a method called rational method. That is the conventional method for drainage system. It has some errors when the catchment is huge, but at the same time, all you need to do is to upscale your safety factors. You can still use rational method. In this class, we're going to use rational method shortly. I'm going to teach you how to use rational method. My friend in Asaba, Engineer John, Engineer Jeff Conn Associates, that's why he used the rational method too. But what he did was he optimized it. You know, we engineers, we always talk about optimization. Optimization so that your design can fit into a higher return period of rain, a higher, let me use the word, a higher a higher safety factor. You know, when something is, when you know that 1 mm when you know that 1 meter pipe will do, nothing stops you from providing 1.2 meter. Okay, but you cannot provide 0.9. You cannot provide 0.8 for something that is 1. So you must move in the direction of safety. You must play safe. You must play safe. So using the rational method, all you need to do is to add some, optimize the system, or optimize your system. You know, and that's what SWIM does for you. SWIM is an application for drainage design. SWIM does not do the design for you. You are the one to do the design. But SWIM will help you to model and to simulate. I always tell people, there is no software in the world that can do design for you. I'm here to see one. What software does for you is to model your design. Some people will say to draft it. That's the same word. Because drafting is just a model, a visual model, a 2D model or 3D model. So then another thing that software does for you is to simulate your design. Simulation means I want to know if my design will work in Abeokuta and work in Maiduguri. So I will simulate it for Abeokuta. I'll take it to Maiduguri and I'll simulate it. Okay? If you work for Lagos, there's a flat land, or Bayelsa, a flat land with high rainfall intensity of between 130, 140, 150, depending on the season. And Bayelsa or Benin, you're getting about 140, 150 again. If my drain will work in that case, when I go to Maiduguri, where you have almost half of that, which is about 80, what kind of drain will work? Okay, in Lagos, you have many outfalls, many discharge points. You can discharge anywhere. But in some areas, you might not discharge any area. You might have to go at the closest lake, at the closest outpour point to discharge your drainage. Then what is the length? How far will that water travel? How far will that storm travel to access that place? And mind you, as it's traveling, as it's going, is building up. In other words, is involving more catchments. Is taking in more tributaries are coming. So these are what you do. So for you to visit your site, if you visit your site, what is the area of the land? What is the map? Do you have the detailed elevation model? What are the elevation? What are the slopes? So these are what you ask for in terms of the survey information. Please take notes. The second thing is catchment characterization. Look at these two catchments. The runoff in the one on your left is about 10%, because 40% of the water that comes in here will go back as evapotranspiration. 25% will go in as infiltration, because the soil is good. It has a good hydraulic conductivity. Yeah? Then 25%, another 25% will go into deep infiltration. Only 10% will generate runoff. So you see, if you are putting drain here, it can be a small drain. But look at a built-up area. 55% runoff, 55 massive percent, only 5% deep infiltration, 10% shallow infiltration. So you see, if you are designing here, you see that the size here will be so huge, so massive. Why the size here will be so, won't be that much. Then look at this pavement now. The runoff this one will generate is different from the runoff this one will generate. It's different from the runoff this one will generate. And it's different from when it is asphalt, like this one, or interlock mixed with, this is a special type of interlock. You know, this one will be like half will infiltrate, half will overflow, that kind of thing. But so if I ask you now to give me the peak runoff of all this area, I can tell you that the peak runoff of this area is about 0.4. This area is about 0.3. This area is also 0.3. This area is about 0.3. This area is about 0.2. And this one that is all asphalted will be around 0.6. The one that will generate more runoff will have a higher peak coefficient. Now, I want you to see this peak coefficient thing as safety factor. You know, we call it a contributing area. We talk about contributing area. Which area is contributing to runoff? So that area is all included in one function, and we call that function peak runoff factor, or peak coefficient, runoff coefficient, sorry. Okay, so here you see, sorry, this is what we're talking about. This is the area, then, okay, let's just go ahead. So you do your design, you digitize your network using software. Then urban hydrology, this is what you have. I don't want to go on through all these things. When we come to the software, you see all this. So in urban hydrology, you talk about rainfall intensity. Now let's talk about urban hydrology. If you are doing your design, you need to know, what are you designing for? Are you designing for drainage? Are you designing for flood?
There is often for issue, you know.
So are you designing for drainage? Are you designing for flood? If you're designing for drainage, you use a smaller safety factor. If you're designing for flood, you use a higher safety factor. If you're designing for a drain, you use a higher safety. If you're designing for flood, you use a higher return period or higher flood frequency. And let me explain what this thing means. There is a particular rain that comes in a year that is bigger than every other one. Now, how frequent does that rain comes? Is it every year? Is it every 2 years? Is it every 3 years? Is it every 4 years? Is it every 5 years? Depending on the number of years it comes, that becomes the return period. So in designing for flood, it is that particular rain that you use. In designing for stormwater, you use that particular high intensity rain. So you're going to hear people talking about 5-year flood, 10 years flood, 25 years flood. Whether they say 25 years flood or they say 25 years rain, is the same thing. Or they say a rain with a return period of 25 years, it means the same thing. Now, in water, as a water engineer, as a water consultant, you can there are terminologies you use, but you must know that some of them are used interchangeably. If I return period and I say one is just the inverse of the other one. Okay, this flood has a high frequency. It means that it occurs very often. It means that the return period will be very low. I will still come to that. Okay, so now let me just take sorry, 1 minute. Okay. Somebody sending me a message. Please, everybody should join. We've already started the training. Okay, so you see flood frequency analysis. You must do your flood frequency analysis. You don't just say 100. When I mean 100, I'm talking about 100 for Abuja, an average. But when you are designing for a 50-year flood, I'm going to use that 100 years and extrapolate it. And by the time I finish it, I might be getting 150 mm or 120 mm for a 50-year flood. But a 10-year flood or a 5-year flood will give me 100 mm. So it means that in using your flood analysis, you must use the highest flood based on what you're doing. We'll still come to that. I will show you when to use 10 years, when to use 20 years, when to use 15 years, when to use 25 years. Now, the next thing now is time of concentration, duration of rain. In design, we use short-time rain. You don't use long-term rain. I'm not a Lagos person. I don't stay in Lagos. But let me tell you one thing that you must have noticed in Lagos. The rain that will cause problem in Lagos is that rain that falls for 20, 30 minutes. The rain that will fall all day, it hardly cause problem. So in doing your rain intensity, you must use the rain within, normally in the standard, we use 15 minutes. We talk about 15 minutes rain. You must use between 0 and 20 minutes. Because if you notice, if you have been observant, that is when you have the highest intensity of rain. Between the first 10, 15 minutes, you have the next thing now is your IDF curve, your intensity duration frequency curve. In other words, what is the intensity of rain in this area? You now do it for all the areas or for all for a particular city. Every particular city has its own IDF. And that is what I said in our highway manual, which I have shared with us. You see the IDF, this is Nigerian Code of Practice. You see the IDF curve of all the cities in Nigeria, done by the Federal Ministry of Works. Let me just open the first one and the second one and just show something. Okay. You can see here. Look at the page now. This is Federal Ministry of Works, 2013. This is the Drainage Design Manual. I've shared it with us. You have it. It's your own. Then if you go to volume 2, this is Yola. So if I'm doing drainage for Yola, I must consult this. This one is for Zaria. This one is for, okay, and so on and so forth. I want to bring other cities. Sorry. Okay, this for Yola, this for Zaria, and other cities. What are the other cities now? Okay, let me open it. Okay, this is for Makurdi. So if I'm doing for Makurdi now, I will come here and I'll see that in Makurdi, the 15-minute rain in Makurdi is expected to generate an intensity of about 80-90 millimeter per hour for a return period of 1 year. This is 1 year return period. But if it's 100 years, nobody can design for 100 years. 100 years is the last flood we have in Nigeria in 2013 was a 50-year flood. I was in Germany when it happened, but 2012, sorry. That was when I was finishing my master's. I heard about it. I heard that nobody was able to cross through Lokoja for 2 days. I heard that they asked people in Bayelsa, old people in Bayelsa, and they said that the last time they had such an incident was about 50 years ago. So when I heard it, my mind just told me, okay, this must be a 50-year flood. Now, where I stay in Abuja, I have stayed there for like 5 years. I noticed that every 5 years, there's always a particular flood event that comes and it will enter people's house. I've noticed it. In a year, it might not happen. The next year, it might not happen. But at least in every 5-year cycle, you see water entering people's house. In Lokogoma, those of you staying in Abuja in Lokogoma, it has become a yearly thing for drain, and it's going to be worse. It's going to be a month. It used to be a 5-year thing in Lokogoma 10 years ago. I was part of people that built one of the estates in Lokogoma, FRSC estates. Then people have not moved in there. Developers have not moved in. So there are a lot of free areas in Lokogoma. So most of the drain were entering the drain system, they were percolating, sorry. But now, if you go to that Lokogoma area now, everywhere is built up. And people are no longer using green areas in their compound. They are using interlocking. And they are using hard concrete. So once it rains, everybody's water will go to the drain, to the public drain. And before it gets to downstream, everywhere is flooded. So the more they are building houses in the Lokogoma area, the more they're going to be having flood drainage. They're going to have flooding. Why? Because number one, they are not following the building requirements. People are not observing green areas. You know, you can use interlocking. I'm not against using interlocking, but you should do it in such a way that at least 50% of every water that comes into your compound must percolate. Only 50% or even less should flow to the public drain. Number two, the designers, FCDA, 10 years ago, federal government said they don't have money. They're no more sponsoring infrastructure design. As far as I'm concerned, they're only doing the major infrastructures. Private developers went into PPP, into drainage, into infrastructure development. And guess what they are doing? They are undersizing their drains. I have seen it. And that's why we are doing this training anyway. There's a lot of undersizing of drain going on. A lot of undersizing. And when you undersize, you will see the implication. Number three, they are using the wrong parameter to do their design. I will explain. In engineering, we use worst case scenario. You must use the worst case. You must look at the worst case. What is the worst case? Precipitation in Abuja is 100 mm, but not every time. Once in a while, it goes to 120, 130. Will you use 100 to design? No. You have to use the worst case scenario. So that worst case scenario is what you have here. It could be, I don't know if you are seeing my screen. I know you are seeing, I'm sharing my screen. It could be 2 years, it could be 5 years, it could be 10 years, it could be 25 years, it could be 50 years. Nobody goes beyond 25 years, as far as I know, because the higher the years you go, the bigger your drain. So be careful. If your state governor calls you and asks you to come and do an urban drainage design, don't go and use 50 years design. You'll be in trouble. I'll tell you why. If you use a 50 years design to do your drain design, somebody that uses 5 years will get 1.2 mm drain. You that use 50 years, you'll be getting 2.5 mm drain. Now, when you present your design to your governor, the person that used 5 years might have a bill of 2 billion naira. You will be having a bill of 6 billion naira. And I don't think your governor is going to accept your design because you're an engineer. So you have to be careful. So the return period is a political decision. Even my professor that taught me in Germany told us that it's a political decision. It's a political decision. It's a decision that must be made by the policymakers. The governor needs to say, like Governor Kowa of Delta State, I commend him. I've gone to a Delta State, I've seen those drains. Delta has been a mess for long. But you need to see what they are doing now. They are building big, massive rain. I only wish my governor, the Abia State governor, will come and invite me. I'll tell them what to do in that area markets that is giving them problem. I want to know what it is. It's very simple. It's for them to do a huge drain and discharge it after Aba City. There's another city called Osisioma going towards Port Harcourt, but that's another day. But I'm just going to give an idea of mistake that people do. What the Delta State governor now is doing is that the drain in Asaba, they are discharging it directly into River Niger. Is going directly into River Niger. Yes. So it costs a lot. So you see that it's not every governor that will bring out money and say, okay, I want a good quality work. So the return period is a political decision. So, but the standard, the German code and standard gives you a guide. If you are doing, let me quickly find the material and just show us what I'm talking about. Somebody say I'm far away from the mic. Okay. I'm far away from my mic. Okay, I think you can hear me now. I'm trying to make it loud as loud as possible. Now, let me look for a example of what I'm talking about. Let me see if I'll find it here and just show us an idea of your design lifespan. Let me just tell you what to use, depending on the number of years, based on the standards. Stay with me. Let me look at hydraulics, sanitary sewer, or hydraulics. Look at my hydraulics. Okay. No, it's not here. This is not here. This is hydraulics. It should be in, just hold on. It should be in sanitary sewer. I'm going to explain all this thing to us. Okay. Then it must be in this one. Okay, it's here. It should be here. Good. Oh, I can't find it. Okay, the point I'm trying to make is this. If your design is in the rational method, then rational method. Okay, good. Okay, you see, if you look at this place, you see that it's a rural area. If you are designing for storm, which is normal thing, your drain, the one we call gutter in local parlance, okay? The gutter, the one we do in front of your house, okay? That's you're designing for storm. You know, when you're designing for rain, your design is if rain falls, what the size of the drain that can take the water into the bigger drain, from bigger drain into the river or outpour point. Now, the standard says for residential area, you use 2 years design period, return period. For city centers, you use 2 or 5 years. Then if you are designing underground facilities, you use a 10 years return period rain. But if you are designing for flood, if you are designing, if your aim is to design against flooding in a flooding area, and you are asked to, as engineer, to come and design against flooding, in residential area, you're going to use 20 years. You're going to use a flood of 20 years. If it's a city center, you're going to use a flood of 30 years. Then if you are designing underground railway or underground system, or underground houses, or houses that has basements, then you're going to use a 50-year flood. What this number means is safety factor. And this number is a function of cost and is a function of size. What this 10-year return period means is that what's the maximum rain that will occur in 10 years? Or what is that maximum rain that is so intense that it occurs only once in 10 years? So that is the value I'm going to use. In Lagos, in other big cities, they have those challenges that once in a while you hear that there's a flooding, there's a high intensity rain, towards August and September. Some people from places is June. In Europe, they have their own season. In America, they have their season. So what we're just saying is that it is the value of that high intensity rain that you are expected to use. Okay, so I think I have shared 4 materials with us. I want us to download the rational method, the swim presentation on hydrology, the swim presentation on sanitary sewer, and then the hydraulics is not important. Then let me also share this one. So I'm going to give us 5 minutes break for us to download all our materials. If you have problem with the what I've shared on the net, on the cloud, this is the opportunity. So this is 4:12. We're going to have a 5 minutes break. Please download the whole material, because now we're going to start the design proper now. I'm going to the design. I'm going to do a case study now, rational method case study. I'm going to start with the rational method case study. So I want you to download the whole materials now. Which I'm going to send to everybody. So, gentlemen, welcome back to this section. I hope the class is not boring, but if it's boring for you, forgive me. After now, I'll go into action. I just want to run through the material. I'm not going to emphasize on it, but I'm going to run so that I can highlight the key areas so that when I mention a term, you will understand what I'm talking about. Subsequently, I think I'll be sending this material ahead of time so that people can read and come to the training. Now, hydrology. Hydrology, good. In sanitary sewer, what constitutes the sanitary sewer or the runoff from dimensioning is what we call dry weather flow and runoff. Now, this runoff is, when we say dry weather flow, I'll be using some terms that everybody will be conversant with. Dry weather flow is that flow when there is no storm events, when there is no rain events. The water flowing in your sanitary sewer is absolutely when there is dry weather flow. Dry weather flow means the weather is dry. But this ROW you have here is what I try to explain. It's called unavoidable stormwater inflow into the sanitary sewer. It's not unavoidable. It's about 0.2 to 0.7 liters per hectare per seconds. It is just like a safety factor to say my sewer is not waterproof. There could be other water that are flowing inside the sewer. So in order to be safe, I will include some ghost water in quotes or parasite water. But for the storm sewer, the separate sewer, the flow in the separate sewer is just equivalent to the runoff, or which is stormwater flow. Then for the combined sewer, it is now the stormwater flow plus the dry weather flow. Now, there's something I want to establish here with every one of us. That is the fact that when I say storm is talking about hydrology, it's talking about rain intensity. When I say sewer, I'm not talking about the foul sewer, what is coming from the household. I want you to know that. Then for the urban hydrology, it is the rain, it is the runoff, collection of stormwater in a sewer, and then the discharge. Then in a rainfall, the parameters that can be used to describe rainfall are the duration. Rain intensity must have a duration. Then it can have a height. Then it must have intensity. Duration is different from intensity. Duration is how long. Intensity is how intense it is. And then it must have frequency. How frequent does it occur? And the frequency is the inverse of the return period. Just take note of that. And intensity is just the height over the duration. If the height over the duration is high, that means the intensity is high. You know, how do you measure rainfall? Those days, there's what they call rain gauge. The rain gauge, you put it outside and the rain will be falling. And when rain falls, you now raise a rain gauge, which is more like a glass jar. You now check how the rain what's the height of the rain relative to the time it has fallen. If you divide both of them, it will give you the intensity. So when I say frequency, intensity, duration curve, I'm only talking about the intensity of the rain, IDF, intensity, duration, frequency curve, okay, which I just demonstrated to us. I showed us what it looks like. I just showed us what it looks like from what was done from the highway design manual. Rainfall, intensity, duration curve. What does it look like? I think I've shared that with us. Okay, good. This is what it looks like. This is what it looks like. It's a chart that shows you the duration of the rain. And then the vertical shows you the intensity. Okay? In other words, duration, the millimeter height, how high, if you put a glass jar of water of a certain calibrated size, how high will the water rise in that jar? And gentlemen, some of us have watched CNN. Before you declare, when you want to forecast a flood, what gives you an idea of flooding is if you measure in the last 1 hour that the rain amount of rainfall have exceeded about 100 mm, then they will forecast flood. How do they do it? They do it by knowing that once the height of water crosses a certain level, by the time you multiply it by the catchment area, it will lead to flooding. That's how they do it. That's why they tell you that in the last 1 hour, they have experienced 150 mm of flood in Oklahoma. And by the charts, any rain that exceeds 150 mm in 1 hour, there will be a flood event. Why? Because by the time the water from the highest catchment will come downstream, the drain will not be able to accommodate it. But if they record 50, 60 mm, they know, okay, it's still manageable. But once it exceeds a certain threshold, they give alarm. That's how to do early warning system. That's all the magic behind an early warning system. Is your ability to know the height of water relative to the intensity. So we are back to we're on hydrology. So that is it. And then for a rain of 10 minutes, we usually assume a baseline. This is a baseline this is a formula, but this formula is no more being used now. I'll give us the latest formula, how to calculate it. But we assume that if you want to get the runoff, you just multiply 166.7 multiplied by the intensity of that area. It will give you the runoff, which the unit is in liters per seconds per hectare. So it now gives you classification of rain. Any rain that the R is less than 7, the value is about 650 liters per hectare, is called a weak rain. Then the heavy rain, the R value is more than 21, and this is the value. It means the contributing area is about 15 hectares. That's no big deal. Then this is their own rain. This is European rain intensity fluctuation curve. Their rain pattern is different from our rain pattern. If you look at our own is more like this way. Their own is more like this way, but it's all the same thing. It's still the same thing. The higher the duration, the lower the rainfall. If you remember the one I showed us for our own, for here in sub-Saharan Africa, down south, as they used to say. Don't worry about this formula. This is an old formula. This is an old formula that I use. But these days, what we use is what we call Costra table. We make use of the Costra table. All these formulas have been put into tables. So we no longer use all these formula. But what I want you to understand is that this formula will take care of these three things. It will take care of the intensity of the rain, the frequency of the rain, and then it come up with the R. So when you see this arrow subscript D and N, it means rain intensity as a function of the duration and the frequency. N is the frequency. So when I say the rain intensity is 100 mm, it's incomplete. I must tell you is a 10 minutes rain, is a 15 minutes rain, and then is a 2-year return period rain, 5-year return period rain, 25-year return period rain, 50 years return period rain, or 100 years return period rain. Those of you that are civil engineers that design dams, if you are designing dam, you're going to use 25 or 50 years. Why some of our dams toppled, had issues in 2012 is because most of our dams, because of political consideration, we design based on 25-year return period. So if a rain that is 50-year return period comes, it will topple our dams, but not earth dams anyway, because earth dams must not be toppled. Once it's toppled, it's gone. Okay, that is that. That's just a small digression. So the next thing now is we make use of time factor. So it says now, look at this. It says in Germany, for a rain period of 15 years and a 1-year return period is between 90 and 130 liters per second per hectare. You know what I told us? It says in Stuttgart, which is my city, is 126. I told us in Abuja, we use about 100. In Lagos, from the chart, you have the chart, you can look at the charts. You can look at the chart. In Lagos, Lagos is around 140. Okay, let's demonstrate this. I think too much talk. Let me open Lagos, open Abuja, so we can see it. 15 mm, sir. Okay, 15 minutes rain. 15 minutes rain. Don't worry, you get what I'm saying, sir. Hamid. I say like what you have here now. The value for the one we just have here in Germany, he says this arrow 15.1 means is a rain. I took it after 15 minutes, and the frequency is 1. What a frequency of 1 means that the rain occurs every year, once every year. Okay, once every year. Let me use the whiteboard and demonstrate something now. Okay, let me share a whiteboard. Okay, this is my whiteboard. Test. Okay, now watch this, gentlemen. There's what we call frequency. Frequency is the inverse of the return period. Now, when I say, like the one I say now, I say R underscore 15 underscore 1. It means that this rain occurred, I took the value after 15 minutes of rain, and that should be the maximum anyway. Not only the maximum, but the optimum. Gentlemen, once it starts raining, in the first 5 minutes, the rain will be so intense, but you don't take the value then. You take the value after 10 or 15 minutes. That is when the after 15 minutes, the rain will likely start coming down. So that will not be the case all the time, but this is a model. That is what the standard says you should take, the cutoff point you should use. Now, if a rain happens every year, the frequency N would be 1. If the rain happens once in 2 years, the frequency will be 0.5. Yeah, you get it now. If the rain happens every 5 years, the frequency will simply be 1 divided by 5, which is what? 0.2. So for any frequency, it's going to be the inverse of the return period. That's the formula. Now, what it means is that if a rain falls every year now, if I say I'm designing for a 10-year return period, in other words, T equal to 10. I'm talking about, a 10-year return period rain is more intense. It means it is that heavy rain that occurs once in 10 years. It means that the N is now 1/10, which is equal to 0.1. What it means is that the probability of this rain falling in 1 year, in a year, is 0.1, is 10%. That means the likelihood of falling is low. We audit probability in school. Probability, if I say probability of 0.1, and a probability of 0.9, you know that 0.9 means there is a 90% chances that the thing will occur. Why 0.1 means there is a 10% chances that it will occur. So 0.1 is a low frequency rain. It means this rain does not occur all the time. It occurs only one. But the return period will be high because it's the inverse of the other one. I will not go more than that, but I just hope that we'll really understand what that means when it comes to return period and this. So we'll move on. So for peak runoff coefficient, when it rains, there will be drifting, there will be wetting, there will be evaporation. At the end of the day, after all losses, there will not be a factor that determines the one that goes to the drain. And that is what we call the peak runoff. For instance, a gravel path, you know what I mean by a gravel path? A gravel path is where you pour gravel, a normal ground, has a peak runoff coefficient of between 0.15 and 0.3. While a roof, a clay roof, a roofing sheet, a slated roof, has a runoff coefficient of 0.95. As I said, you cannot say 100%. You cannot say it is 1. Rather, you say it is 0.95. That means 5% is for losses due to what I don't know. Maybe water splashing on the wall of the house, water, wind carrying some of the water, or just or some returning back if it's a hot weather. As the rain is falling, some are evaporating due to already hot surface. So you see that the intensity depends on the impervious area, the imperviousness of the area. The surface type is very important. Then the slope, then the intensity of the rain, then the type of soil and vegetation. Gentlemen, what we are talking about here is how do you compute what flows into your drain? It's a function of the area, the type of soil, the slope of the area, and many other factors. Then if you read this through, it will tell you the relationship between the impervious area and the slope. The higher the slope, the higher the runoff coefficient. A slope of less than 1% has a runoff coefficient of 0.55. The same material with a slope of 3% has a runoff coefficient of 0.63. It means the more slopey an area is, the higher the runoff coefficient. So runoff coefficient varies is directly proportional to slope. Now look at this. If there's a rain event here, starting from here, this is street inlet. You'll agree with me that by the time it gets to the street end, the rain has built up. This is like building, it's building up. So runoff builds over time. That's why runoff is a function of area. The catchment area, the bigger the catchment area, the higher the runoff coefficient. And the more it goes downstream, the bigger it becomes. So runoff now is a function of why do you determine runoff for urban drainage, for stormwater drainage? It is the intensity multiplied the time factor multiplied by the coefficient of runoff multiplied by the area. But if you put up all these ones together, they will give you a simpler formula, which is just area times runoff times area times the intensity, sorry. So you can put all these three together. It will become what we call peak runoff coefficient. If you put these two together, it will give you just the time factor. So after that, let's go to the urban drainage. Let's follow it up with urban drainage. So urban drainage. Okay, we are somewhere here under urban drainage. So let's do an exercise, and a simple exercise now. For instance, now there's an area with the catchment area is 100 hectares, but the impervious area is 45 hectares. These two, how do we come about it? It means that the runoff coefficient is 0.45. This is an area, if you measure the area physically, you see it is 100 hectares. But the area contributing to runoff, the area that you use to multiply your intensity to get your drain is actually 45 hectares, because only the impervious area contributes to runoff. Only the impervious area, only the area that are paved. In other words, the area that will not allow water to percolate, that is the area that contributes to runoff. Now, the population equivalent, the population of the area is about 10,000 capita, 10,000 people. And the water consumption of this area is about 150 liters per capita per day. And we assume that infiltration water is about 5 liters per second, which is okay. And then the time of flow is 30 minutes. This time of flow is an arbitrary time which gives you an idea. When will the water that falls in one part of the catchment gets to the end of the catchment? In other words, if it starts raining now and water falls in front of my house, how long will that amount of water, assuming I attach something to that water, how long will it take the water to flow into the bigger drain or the outfall? That is what we call time of flow. Okay? So that time of flow is so important. That's what contributes to runoff. Because if it starts raining now and I'm having small amount of water, if the water from the upper catchment or the furthermost catchment have not gotten to this place, then it might not generate flood until it gets here. That's when you now see flood. So I need to measure, say, how long will it take my water, for instance, the water from my compound, to flow into the main drain provided by the FCDA. So that is what we call time of flow. So now, if you do the calculation, you calculate this, you now say this multiplied by this. So how do you get this? You convert it to liter per second. Okay? For instance, the wastewater flow is 150 and the population equivalent is 10,000. So what it means is this. I will now go to my board. So the water demand per person, water demand is 150, sorry. Okay, and the population of people, of persons that are contributing to that runoff is about 10,000. Okay, therefore the discharge, this 150 is, the unit is in liters per capita per day. Those that attended the water training will understand what I mean. This is the amount of water you assigned for one person per day. We assume that each person will not consume more than 150 liters of water. And I told us at the beginning that when you're doing sewer design, you assume that what somebody takes is what he'll produce. So in this case, we're also assuming that the amount of wastewater that will be generated is equivalent to the amount of water that you are taking. In places like Germany, they don't charge you for water and charge you for wastewater. They just charge you once. They assume that the water you are taking is what you will produce. So because of that, once they are billing you €2 per cubic meter of water, €5 per cubic meter of water, €2.5 is for the water you are taking, and €2.5 is for the wastewater you are going to generate. So they just take it once. So in this case now,
that's not possible, sir.
It's not what?
Sir, is it possible that the water of the one you take in, Because in the American system, I think they adopt 0.8 as 80% of the water.
God bless you, sir. I love that contribution, sir. That is why I said, but in payment, now you're talking about in design. I agree with you. What you are doing now, you are assuming that if somebody takes 100 liters of water,
Okay.
he will charge 80 liters.
Yes.
Meaning, you're assuming that he will use 20% either to do gardening.
Yes.
20% will give it to his children who are going to school.
Yes, something like that. 20%
is unaccounted. Maybe he's corrupt. He's a corrupt guy. He will eat 20%. So it's good. That is their own standard. Okay, but in design, you can also do that. But to play safe, use 100%. And you know, as an engineer, if you are using 80%, 0.8, and me, I'm using 0.9 or 1.0, I'm safer.
Yeah.
Because in Nigeria, people will buy pure water and come back. Somebody is going back to Marabanyanya. He will pass through his office, the Minister of Water Resources, and use his rubber and fetch some water and add to what he has, what water board is giving him.
Okay.
So instead of going lower, in our own case, we should go, okay, if you can't go 1%, 100%, let's go 90%. But you're absolutely not that. Because you are following the American code and standard. That's why code and standards are important. So in the American system, after doing this calculation, you multiply by 0.8. That's what engineer is saying. And I agree with you. But that's American. Yes. So now, to estimate, this is the water, is an estate or a district that is made up of 10,000 persons. And the water demand per person is 150. That means the total water, their intake, which automatically is their outtake, if there's anything like that, becomes 10,000. 10,000 times 150. Okay, and that will give you 150, 0.0000.
No.
0.
15 million.
Now, let me tell us this, and this is worth noting. This is a very key thing. The chart we are using, or in both urban drainage design and water distribution design, you must convert your unit. This unit now is in liters per day, but you must convert it to liters per second, because liters per second is the smallest unit. Okay, remember 1,000 liters is equal to 1 cubic meter. Are you with me? Sorry, I can't do superscript here. I can't do superscript.
No, it's okay.
I can't do so. There is no unit that is lower than 1,000. That is lower than liters. Liter is the lowest unit. Okay, so now you have to convert your unit to liter per second for you to be able to use our chart, or any chart for that matter, or any table. So in converting this unit, if you remember, converting one day to seconds, 1 day to seconds is equivalent to 24 by 60 by 60, and that will give you 86400. Those that came from my last training will already know about this. So this is 86400. Some of us that all did mechanical and civil engineering, engine 309, hydraulics, we all did this. Something like hydraulics, we did this. To converting 1 day to seconds is this. So if I'm to convert this liter per seconds now, that means it's going to be 150 divided by 86400. What is that? The unit now will be in liter per second. So we have 150, divided by 86400. What happened to mine? 86400. That will give you 17.4 liters per second. So it means that, gentlemen, this is a common thing. It means that for a catchment that has 10,000 people, the amount of wastewater they are generating in 1 second is about 17 liters. It makes sense. It makes a lot of sense for me. It makes a lot of sense. So this is 17.4 liters per seconds. It means in a catchment of 10,000 persons, in every second, the amount of wastewater, sanitary wastewater, foul sewer, the amount of water flowing in the foul sewer network, or the discharge, or the flow, all these three words mean the same thing. The discharge is 17.4. The wastewater flow is 17.4. The sanitary flow is 17.4. The sewerage flow is 17.4. So I can use like 5 words. They all means the same thing. So now, this 17.4 now is now what I will use to dimension my size and say what size of pipe can take this. If I know the slope and I know the pipe characteristics, I will get my pipe size, and I have the chart with me, and that's what I'm going to give us now. That chart is a magic. Is one of my takeaway from my water resource training in Stuttgart. That chart is because you can't start using Manning N 1/3 times arrow square times any times Reynolds number. You know, there's one long formula people use, or you develop a spreadsheet application for it. But with the charts, which we all did as engineers, those of us that are in civil engineering, if you are doing pipe size reinforcement, if you are doing column design, you know, there's this chart we always use to do all these things. Okay, there's this chart we always use to do all these things. So here, this is the chart. This is now this chart. You now take this value and now go to your pipes, your chart, and you now determine what size of pipe that is. Now, I'm going to show us this is how they got this. Let me go to this. We're on urban drainage. We're done with hydrology, so I can close it. So this is how they got 17.4. Are you with me? So the wastewater flow is what? 17.4. But I told us that you need to add a safety factor. So wastewater flow now is 17.4 based on 10,000 population equivalent, based on a catchment area of 100 hectares, but impervious area or contributing catchment of 45 hectares. You cannot use 100 hectares to design. We use 45 hectares because 45 hectares is like the actual area that cannot allow water to penetrate, and that becomes your impervious area, or that becomes what you call your contributing catchment, okay, or riparian catchment. That becomes your effective watershed. I can use like 100 words to explain them. They are all the same time. I'm a water engineer to the core. So any of these words you use, I understand what you're talking about, and that is what some of us that are coming to this field should also know. You must use the terms. You must speak like a water engineer. So when I say contributing catchment, when I say the paved area, when I say the equivalent paved area, when I say the impervious area, or when I say the peak runoff area, the peak area, I'm talking about the same thing. I'm not talking about that area that I know that this is the area that if water falls, it will not flow into the soil. It will not percolate. It will not evapotranspirate. It will generate runoff. It can never be 100%. It will be some percentage, which is a function of whether that area is a green area, whether that area has a good soil, okay? Whether it's a sandy soil. If it's a sandy soil, the hydraulic conductivity is high. That means water can flow in easily. So these are some of the factors. But all those factors are all embedded in what we call the peak runoff, which I've explained to us, which is this formula. All of them are not incorporated in this peak runoff. So when I say peak runoff, it means I have factored in soil characteristics, land use characteristics, land use vegetation cover, slope, many factors, intensity of many factors. At the end of the day, all I need to do is to multiply it by the total catchment area. So here now, after getting 17.4, I now had to add it 5. This 5 now is more like saying, I am not sure that it's only sewer that is flowing in that pipe. Maybe the sewer will break, water will go into the pipe. Maybe there is some calculation error. So let me just add 5 as infiltration water. So if you now add 5 here, you now get your dry weather flow, DW, now becomes wastewater flow plus infiltration flow. That will be your 22.4. Okay, good. Now, you now say, here now, they now say the critical flow is now 12. Okay, based on the time of this is now critical. So you now multiply that critical by 45, which is now the impervious area. It will give you 540 liters per second. Okay, they are using the formula I showed us before, but I'll come to that. So this 540 liters now becomes your stormwater flow. Are we together? This
on the same page.
Sorry?
Sir, I'm not seeing the screen. I was on the other one. The water demand will just finish. Are we there?
Yeah, can see it now. I didn't share my screen.
Okay, I'm not seeing it.
Nobody said a word all this while. So now, if you look at this now, you see that we have gotten the wastewater flow. The wastewater flow is what now? 22.4. And then the intensity now, based on your IDF curve, we find out that the intensity of rain in that area is about 12 liters per second per hectare. So we now multiply by the impervious area. It gave us 540 liters per second. So this value now is your stormwater, is for storm. Why this value is for your sewer? Take note. Okay. My voice is not my high. I think I will okay. Give me 1 minute. Let me work on my voice, gentlemen. Just give me 1 minute. Let me bring it. Okay. Is it better now?
Yeah.
Okay. So we'll go this way. Now, I want you to take a look at this. I told us in the beginning that there's a sewer design and the stormwater. Now, how do I get my sewer? The sewer flow, which is the wastewater flow. It is simply what is the population equivalent of that area? Okay, multiplied by the water consumption. Okay, that's what we did. Multiply by the water consumption. Look at it. Water demand is 150 liters per capita per day, and the population is 10,000. So automatically, the wastewater flow or the wastewater that will be generated is the specific value times the number, which is 150 times this. But then I have to convert it to the lowest unit for me to be able to calibrate it. You know, in model calibration, in modeling, you must use the most discrete value. You must calibrate based on the minutest, the simplest, because model performs better when they are at when there's discretization. So this is it. So I got 17.4. For the rain, we found out that from our chart, we found out that that area, that the rain intensity in that area is about 12 liters per seconds per hectare. You know, if you convert 100 mm per hour, if you now average it, convert it to liters, convert it to seconds, you could get something like this. So now, and the area this rain is falling is 45, is the area actually, the area is 100 hectare ab initio, but the impervious area is about 45 hectare. That means you should know now that the peak coefficient, that the peak coefficient is about 0.45. Think about it. I told us in Abuja, I believe Abuja, they use 0.5. Why? Because the drain in Abuja, they didn't design the drain that 100% of the drain will flow. That's why if we don't gauge how people are developing Abuja, if we don't look at how people are developing their individual plots, making sure that they observe green area, making sure that they use, if they are using, nobody should use paved area. You must use at least interlock so that some level of water will still percolate. And then the city will provide green areas, some areas that water will percolate. You know, water from a district, from a street, it will percolate in an area. In places like Millennium Park, places like Airport Road. If you look at Airport Road, some of you have noticed there's a setback of 150 on both sides, and those two areas are meant to be green, so that if water comes, the water can percolate there most times. That's why some places in Abuja is better. You see, it's better to green. Cities that are not green will likely have flooding. Let me not digress. I'm digressing too much. Okay, now, so if you look at this chart now, if you look at our material now, you find out that the intensity of rain in that area is about 12 liters per seconds for every 1 hectare. So in other words, the runoff coming per hectare is about 12 liters. And then if you now compute this or convert this, if you convert this very well, okay, you will be having 12 times 45. You cannot say 12 times 100. Rather, it is 12 times 45 because 45 is the effective area after you apply peak runoff coefficient, and it's not giving 540. Then if you are to do a combined system, you add up together. But we're not doing a combined system, so we're going to design these two separately. So that's the next thing we're going to design. So if somebody now asks you to size the pipe size for these 10,000 people at a 150 liters per person per day of water intake, which is automatically is water outtake, okay? It means the water they are generating, the amount of wastewater, WW, they are generating is about 22.4 liters per second. Now, you now go to your chart. You now go to your chart, and let me take us to that chart. Let me assume for the first one, we'll be using a PVC pipe. Are you with me? Now, I'm going to send you what we call monograph. There's 0.1, there is 0.4, and there is 1.0. This 0.1 is a function of the pipe. If you're using a PVC pipe, you use the frictional factor is low. If you're using a ductile iron, the frictional factor is about, you use 0.4. If you're using concrete pipe, you use a frictional factor of 1.0. So this frictional factor is a function of the roughness, they call it the roughness factor or the K factor. If you buy any pipe in the market, check on the body, you will see the frictional factor. It is a function of the resistance. It shows you the resistance of that material to flow. So the lower, the better. So for PVC pipe, especially MPVC, they are very, very low. They are smooth. They flow very well. That's why the friction factor is 0.1. So now I'm going to open this chart. I think I've sent the chart. If I've not sent it, it's already in the cloud. So if you open this chart now, okay, this is what the chart looks like. Ideally, you should print this chart on A3 or A2, not even A4. So on this chart, you will look at, let me increase the to 75%. On the horizontal, it is flow, discharge. On the vertical, it is the slope in per 1,000 anyway. And then on the diagonal is the pipe sizes. You can see the pipe sizes. And the limitation for this one is that the maximum, the pipe size is about, the maximum you can use it to design is 1.2 mm. But that does not mean you cannot use higher sizes. But it means the error is much. That's what it simply means. It means the error is more. So you use empirical formula to get it. So if for any drain that's more than 1.2, this chart will help you, but beyond 1.2, it will give you error. That is where optimization comes in, or interpolation comes in, or you go back to traditional method to get it, which is using formula. And when I say traditional method, what are we talking about, gentlemen? Traditional method simply means that A, Q is equal to AV. Oh, we all know that. In some schools, they will say is equal to I, C, then small q. These two things means the same thing. Here, A means the surface area, or the area of the pipe. V is the velocity. Okay. In this case, I becomes C becomes a constant. This constant is just the same thing as our peak runoff. Then Q is the specific flow, which is same thing as V. And then I becomes the rain intensity, Okay, so anytime you ask me to, anytime you want to get a discharge is always area multiplied by velocity. We all know that, and that's why the unit is in meter cube, because meter cube means length times breadth times height. It's a volume function. Just think about it. So so I want us to take a while and download and study this chart. Please, this chart will require two inputs from you.
That'll be meter cube per second velocity, I think.
No, this chart. Yeah, okay, yes, sir. Yeah. Meter cube per second. You're right, sir. Yeah, per seconds. You're right, because it's a time value something. Thank you. Yeah, thank you, sir. Because this is meter cube. This is meter cube per second velocity. So this becomes seconds. Now, let me upload these three charts, and I want us to use 5 minutes and study it. That's actually our second break. Anyway, in those days they call it tea break. You go out, smoking break. You know, during winter like this, the cold is so much that once in a while the lecturer will tell you to go and they'll allow you to go outside and go and resume recording. So now, as we said, we are assuming that our slope is 0.002, which is the same thing as 0.2%, or 2 per mil, 2 per thousand, sorry. I don't know how to represent this symbol, so that's why I did this. So this is what it is. So this is what we're assuming now. So if you now go to our charts now, okay, remember, what are we doing? This is what we're designing. We're designing for this, for a single sewer of 22.4 days, and as well as the stormwater of 540 liters per seconds. So here, 22 now means I read 22 against 2. So it is getting me to somewhere here. So it's falling between 250 mm and 300 mm pipe, 200 mm pipe and 250 mm pipe. So the standard says I should use the 250 mm pipe, which is the bigger of the pipes. So it means
your screen is not portraying what you're showing.
Okay, I think it's on now. Thank you, sir. So now, for what we are doing now, this is what we are designing for. We're designing for 22.4, which is for the sewer, sanitary sewer, for the foul sewer, for the wastewater sewer. It gave us 22.4 for a population equivalent of 10,000 persons at a water consumption rate of 150 liters per capita per day. Of course, we have to put some small factor to comply with the standard, which is 5 liters per second as infiltration water or as parasite water. Then it gave us 22.4 when we converted it to liter per second. Then we did for runoff based on 12 liters rainfall intensity per hectare. 12 liters of rain falls per hectare. That's the intensity we use for the runoff.
Hello, sir.
For the stormwater. Yes, sir.
Since we are using pipe, what do you bring the infiltration rate there?
Is a standard. The standard says, let's assume you're using a pipe that will break one day, and then water will be infiltrating. You know, if your PVC pipe breaks, there will be infiltration water. In Abuja, I know infiltration water is almost like 40% of sewage flow. I know that. Yes, it's an experience. Yes, especially when you have difficult terrain. So the standard says you provide a certain factor of water to take care of that. It's just a factor of safety. So that's why that's how we move from 17.4 to 22.5 by adding 5.
Okay.
It's always there in engineering. In every aspect of engineering, you always add one or two things to make up for unforeseen circumstances. Okay. So that's a good question. I appreciate that. So now 22.4 liters per second. We now went to our chart. What chart are we using? We're using the chart of 0.1, the chart that is meant for PVC pipe. The second thing, what slope are we using? We assume a slope. Normally in design, you assume a maximum slope of 4%. The standard says you can assume slope as high as 4%, and then as low as, I can't know the value now, but it's the standard, it should be about 0.001, depending on the size of the pipe, because every pipe has a threshold slope. There are some slopes you cannot lay some pipes at a certain slope, but that's not for this class. You can consult standards, it will give you those values. So now, 22.4 now is now what we have for our sewer line. Our sewer line, our stormwater line, we got 540 by multiplying the catchment area, impervious catchment area, or the critical area, or the peak contributing area, or the paved area by the rainfall intensity per hectare. Okay, they didn't give us the rainfall intensity in millimeter per hour, but they converted it into an area function, telling us that it is 12 liters per second per hectare. For every 1 hectare, 12 liters of water is falling there. It's very slow. It's very small, I must say. In Abuja, it will be up to 50. It will be up to 50 every hectare. So that means your drain size, by the time you multiply by 45, it means that this catchment will be contributing up to 1,000 liters of water per second. So now, for the sewer design now, for the foul sewer design, we go to our charts. On the horizontal axis, we have liter per second. We go to here, we go to this place, which is the in-between, the chart in between, the in-between 30 and 40, which is about 25. We just assume that. Then we read it against 2, slope of 2. We ended up somewhere in between 200 and 250, and we chose 250. So 250 pipe is what we're going to use there. That's the equivalent of 9 inches pipe, 10 inches pipe, yeah, 10 inches pipe. But remember, 10,000 people, good. Now, in between these two, there are also 2 lines. If I go down, those lines are between 0.6 and 0.7. That means the standard has been met. Why you check velocity is to check. You check velocity to make sure that the velocity is not too slow. If the velocity is too slow, there will be sediment deposition. Things like tissue paper will not flow in your sewer line. That's why you need to make sure that your velocity, in design, when you check, there's what we call serviceability limits, and there's what we call ultimate limit state. So the ultimate limit state in this case is like the pipe size, but the serviceability limit state is not the velocity. So in as much as you have gotten the ultimate limit state, which is this limit state against failure, which is your pipe size, you should also check that the serviceability limit state is met, which is things like cover and things like firefighting. For those who are civil engineers, those who are mechanical, I don't know how you do your own. Pardon me. Okay, so that is that. So you see now that you can for this catchment, a 250 mm pipe is adequate. So how about the stormwater? 540. What size of concrete pipe do we provide? Now, the first thing I do is that I'll go and use the concrete equivalent, the appropriate chart, which is 1 mm. Oh, okay. So this is the chart for 1 millimeter. Frictional factor of 1 millimeter, which is a higher frictional factor because concrete has a high frictional factor. The same slope applies. Why is the same slope applying? Because it is the same place you're going to lay them. Ideally, sewer line goes below, stormwater line comes above, potable water line comes be at the uppermost. That is how to actually place these things in terms of their vertical alignment. In terms of the vertical alignment, the sewer line must be below, and it should be around. It should be between 1.2 and 1.5. Then the stormwater line will be between 0.6 if it's not an open drain. If it's an open drain, then you don't even need to cover it. That means it's open channel to be between 0 and 1.2. Then after that, sewer comes in. Then, of course, potable water line comes by the side at between 0.6 and 1.0. Okay, so now 540 is somewhere here. So we read it against 2. So reading against 2 is getting me to somewhere here. So the pipe size is now 800 mm. I'm getting 800 mm. Look at it, 800 mm. Okay, so this is 800 mm. That's what I got. So for a discharge, of 22.4 liters per second, the equivalent pipe size we got now is 250 mm, which is for sewer, of course, PVC pipe. But for the stormwater, okay, let me put it the way a layman will understand it. For the sewer discharge, we got to 2.4. Then for the stormwater discharge or storm, whatever language you use, we got 540 liters per second. And the pipe size we got, which is of course going to be 100. Concrete pipe is 800 millimeter. So, question, any question? You can unmute yourself. Can you ask me a question? Is it well understood? Is it well understood? If you understood everything I've said now regarding this, please type yes in your chat box. Go to the chat box and type yes. If you understand everything now, can you type yes in the chat box, please? Hello, gentlemen, I'm waiting. Please, I'll only continue when I get when I'm sure I've gotten at least 50% of yes. Okay, somebody say you're moving too fast, little fast. Yes, okay, I will adjust. Thank you, Hamid. Okay, I will slow down. In fact, I'm going to repeat what I said, but I still want to get that yes from us. Only one person. Please, who is on Infinix X5 leads? I don't know. Just right click on your name and rename yourself so I can know who the person is. Just right click on where you see more. But there are questions. Yes. Okay, ask the questions, please. Ask the question. For the unmute and ask the question. For the 22.4, I went to 22.4. Of course, I use a different chart, not this chart. I use the chart, the appropriate chart. And at 22.4, I read it against, say, 2. It's falling between this line and this line. And this line is 250 mm, while the other line is 200 mm. So it means that this one, I'm going to use a PVC pipe of 200 mm for my sewer. Then for the stormwater, I got 540. I also went to 540 and I read it against 2. And I was getting something about 800. It was falling between 700 and 800. So I'm going to use 800. So in using 800, I also read it against the velocity, and I got the velocity of about 1.2. So the velocity is more than adequate. And the drain size I'm going to use is 800 mm. This 800 mm now, you now go and do pi d square over 4 if you're using a circular pipe. Yeah, there's a question. I know I'm here to attend to that question, but you can meet and ask. So far, so good. Kenneth, I appreciate that. Kenneth Asiegwe, he says, so far, so good. Someone say, I cannot get the nomograph. Okay. I will upload it again on this chat right away. Here it comes. Okay, remember for the sewer, I use the one for 1.0. For the stormwater, I use the one for 1.1. I use 0.1 because I'm using PVC pipe, and that's what you use for sewer line. And then for stormwater line, I use the one for 1.0. More question or more thumbs up? Okay, I've sent it. Who is asking that question? I've sent it to you now.
Hello, sir.
Okay. Yeah, I can hear you. Please ask question.
This is Engineer. Hello, sir.
Are you the one on Infinix?
Yes, I told the name now.
Okay.
I said the two pipes, can't they be joined together since they are carrying
That's
water
a combined. No, they can't be joined together, sir, because sewer is the one carrying foul sewer, as the word implied, is the foul sewer, and it must discharge to the treatment plant. But stormwater is the one carrying stormwater, which is not too much polluted. That one normally goes to surface water. So if you discharge this one in the same place, that means you are polluting the water downstream, and people who are using that water downstream will have issues. You know, these are standard. If you pollute, nobody discharges your sewage water, the water that goes to your septic tank in open stream, you can't do that. It's wrong. It's bad. The fishes in the water will die. Those living downstream will get cholera, and they will die too, or they will get disease. So, but stormwater is discharged to, in Abuja, stormwater discharges to Jabi Lake. Discharged to Jabi Lake. So if you go to Jabi Lake, now that's where you see Jabi Lake is neat. Or like in Lagos, those people that live in rural area that shit inside their water, you know how Lagos Lagoon is. I didn't mean they're not defecating inside the water. Lagos Lagoon would have been for tourism, but that would be me digressing. More question. I said, if you know you're understanding the whole thing, just say yes, type yes to encourage. It's a feedback mechanism for me.
Yeah, understand everything, sir.
Right, type yes. Just type yes. Just say yes so that I can move on. Yes, Muyiwa say yes. So now, can you try your hand on this? Can you size the 22.4, the sewer, and then the stormwater? Just see, okay, yes, Safana, Aliyu Kasina, okay. I have 3 years. I need 2 more years to go. 2 more years. So this is where we are. Remember? This is where we are. So we have designed this. Now, what is asking, can't we combine the two? If you have to combine the two, this is what you get. So you look for 625. The question now is, are you using concrete pipe or PVC pipe? With that, you get the bigger pipe. But in Nigeria, nobody does that because it's very dangerous. Some standards or some places does not allow it because those that do it, they have a regulatory system. They have a technology that can filter dry water flow. So once storm water is coming, they will divert it. There's a diversion channel that will divert it. After storm, it will come back. But here in Nigeria, we cannot do it. You see people discharging into lagoon. They are sewer into lagoon. Okay. Why are we using 2% instead of 0.2%? Okay, this 0.2 is per mil. Okay, that's a good question. This chart is not in percentage, it's in per thousand. This chart is in per thousand. But if you are given a slope in Nigeria, somebody will tell you, either somebody gives you a unitless slope or you give you a slope in percentage. Percentage is also unitless. Percentage is unitless. Just that you are referencing it to 100. But in this chart, it is per thousand. So what we did was that we said, let's use the value for 1,000. Look, we change this to 1,000. Okay. Maybe that's what you understand. This is it. I think you understand. The person that asked the question, you understand it now. It's better now. It's better now. It's more obvious now. This is what we did. So we assume here to be 1,000, and we design based on 1,000. Okay, we're going to continue. So that is that. So we're done with this chart. So just look at this. You read this, you understand it. This is your catchment producing water. And then, so this is what I said in the beginning. This is a waterfalls, precipitation. It goes to roof, it goes to traffic. Surface runoff constitutes stormwater. Stormwater will go to a stormwater treatment plant. Sometimes this can be a garden. This can be a big sedimentary basin. It mustn't be a concrete structure. Then after small treatment, the thing will flow into the river. The idea of this structure is to make sure that what is flowing here, in Germany, they have so much standard that the health of their river is measured by the number of fish and the type of fish in the water. Once they start seeing some certain type of fish in their water, they will know that that water is no more healthy. Unlike in Nigeria, so water body you see around us, you can't even see a cockroach inside, not to talk of the fish, because fish cannot survive inside it. For fish to survive inside the water, it means that that water is healthy. So for foul sewer comes from domestic wastewater and then industrial wastewater, and the plus small infiltration water. Then it comes to a wastewater treatment plant. WWTP means wastewater treatment plant. And then after treating it, they will return the sludge, use it for manure, the solid matter, and then the upper matter. After 28 days or 26 days of treatment, passing through different treatment stages, the water will now be discharged into the open stream. By then, the load have been reduced. The BOD have been reduced from 300 or 400 to about 18 or 20. Okay, then with time, as it flows through the water, it will treat itself further. Okay, so this is an example of a combined system. Take a look at this: separate system, sewer system, stormwater system. If you now combine the two, you have a combined system. But then, even on the combined system, notice that when the sewer line comes, if there's no rain, the thing will flow here and go to the treatment plant. But when rain comes, they will shut down this place and then allow it to flow into the open body. It's a very complicated and very advanced technology, which we might not be able to operate it in Nigeria. We don't have the technical know-how. So what is the difference between a separate sewer and a combined sewer? You can see in a combined, okay, you can see a combined sewer. You say wrong connections possible, which is wrong connections. Remember what happened in the, is it Queen's College some time ago? Somebody went and connected their sewer line to their water line, and the girls were drinking bad water. Let me use the word water that are contaminated with E. coli. And with time, some of them developed illnesses. Some of them, I even had some of them died. So there's a possibility of wrong connection. It happened in Lagos. I had it in the news like 5 years ago. Before they now discovered that the water they are having has been contaminated with sewer line. Then infiltration water only in one sewer. This one's a wrong connection possible. So this is just something we can read and understand. I don't have to go through it. How about this one? The same thing. How about this one? The same thing. So you can read all these ones and understand them. Then we're going to the last one before we call it a day for today. Tomorrow is going to be a lot of calculation. So we can spill this thing. So, okay. No, I don't think I have any other thing. I think all we have now is rational method. So let me introduce us to rational method before we go. Okay. So this is an exercise we're going to do, gentlemen. We're going to do this exercise together based on what you have done. Let me see how far we can cover. Any questions so far?
Yes,
Thank you.
we have not checked the velocity on the storm drainage aspect?
I checked, sir. It's 1.2.
Okay.
Look at it, and it's more than adequate. I did, sir.
Okay.
Look at how I checked it. I first of all, okay, this is for PVC. K value 0.1. So let me go for the one. Let me go for the one for. Okay. Sorry. This is the one for PVC 1.0, K value 1. That means this is for concrete. So when I got to 540,
yes.
I even dash in 50. Let it be 550. And I went here. This is 2.0
yes.
to 2. It falls in between 700 and 800. I choose the bigger one, which is 800.
Yes,
Then
sir.
the velocity is 1.2 and 1.0. But I choose 1.0 because it's in the direction of safety.
Okay.
So anything between 0.5 and 5 is okay. But that does not mean if you get 0.4, you discard your design, you condemn yourself. It's when it's getting to 0.1, 0.2, you say, no, this velocity is too low. If tissue paper should fall inside here, it's going to block. It's going to plug the system. Okay? Aim is to avoid plugging. So for you to avoid plugging, minimum velocity must be met.
Okay.
But that's in design. I don't know where I see engineer. That's like serviceability design. The main ultimate design is this 800, which is the pipe size. Thank you for that question. That's a good one.
Okay.
All right. So now, yes, go ahead, sir. Please, your asking question will help me. I can hear you, sir.
Okay, sir. Though I joined lately where you are calculating the discharge.
Okay.
You said Q is equal to AV is equal to ICQ.
Sorry?
Is it the same thing with the discharge formula of Q is equal to CIA? Where
yeah,
it's
the same thing. It's the same thing, sir. What happened in this case is that, okay, very good question, sir. Okay, no, share. Let me share. Very good question. Very, very good question. Now, watch this. Generally in fluid mechanics, Q. Let me give you all the formulas of Q. Q is equal to area times, why did I put times? Area times velocity. Now, because the area has what they call, if it is a dam, you're using a spillway. Some spillways have irregular shape. It can be ogive. So that ogive have a reducing factor. So that means a factor comes in. In our own case, for stormwater, we are not interested in the whole area. We're interested in a particular area that contributes to runoff. So that means we must multiply that area by a certain factor. And now, for stormwater, we are not talking about velocity. Rather, we are talking about one special person called intensity. And that intensity is a function of many factors: a time factor, location, many factors. And then, of course, the area also, the slope of the area, the hydraulic conductivity. So those factors is taken care of a constant called C. And then V. In some text, it will be I times C times more Q. This more Q is called specific discharge, but in real sense, it's actually meter per second. It's velocity.
Okay.
Q is in meter cube per seconds, but small q is in this is fluid mechanics we're talking about here.
Yes, I can remember. Yes.
Just remember, just flashback. You remember there's something like that we did in school.
Yes.
So this one is called specific. That's the word they call it specific. Specific flow. They call it specific flow. But this one is called discharge. Are you with me?
Yes.
So this is it. So what we did now for the sewer is that we calculated the area. For the sewer, you don't make it of area, you make it of population equivalent.
Okay.
You make use of population equivalent. So area, but you can also make use of area, but you make use of area when the place is not built up. And that area will be based on land use. In land use, we have what we call low density area, medium density area, high density area.
Yes.
When you say low density area, you maybe we're talking about 200 persons per hectare, 200 persons, population equivalent per hectare.
Okay.
Okay, let me pause this recording and digress and explain this very well. So now, no, I will pause recording here again. Let's ask questions because I want our opinion. How many of us would like us to spend another 30 minutes? How many people have time for the next 30 minutes?